Okay, dear participants, our sixth geometry topology summer school is continuing with Izzet's talks on rational curves on hypersurfaces. Thank you very much.
All right, thank you very much, everybody, for coming. So let me remind you what we talked about last time. Last time we said that if you have a rational curve, then every vector bundle on this rational curve is a direct sum of line bundles. And then the question that we were asking is that if you have a rational curve and a variety, then there are two bundles associated to this. One is the normal bundle of the curve. The other one is the restriction of the tangent bundle. So like the main question that you can ask is, what is this normal bundle? What is the splitting type? So now I will ask, last time we talked about this in projector space. So this time I'll ask the same thing about hypersurfaces. And you know, the way to think about this is that hypersurfaces are a fairly good test case for general varieties. I mean, of course, every variety is birational to a hypersurface, but you know, but the way you should think about it, most of the techniques and things that you do for hypersurfaces, then you can try to generalize for arbitrary varieties. So, but you know, the hypersurfaces are somehow easier to get your hands on. So the way you should think about this is that, like, you know, you want to know what are rational curves and varieties. So a good place to start is hypersurfaces. So that's what I'll discuss today. So this is setup will be, we'll have a smooth hypersurface of degree D in projective n space, and hopefully I won't mess up my numbers and indices as we go along, but you know, stay awake for it. If I mess it up, then you have to jump in and tell me. So the basic question that you can ask is, what curves lie on X? Okay. And you know, the answer is that surprisingly, even in the case of general hypersurfaces, we don't know the answer. But let's start sort of with some examples. So let's look at first when the degree of the curve is 1. In other words, you have a line on X. So like, you know, you can ask, if I give you a hypersurface, what are the lines on this hypersurface? And this you can actually work out. All right, so now what you do is you form an incidence correspondence. So you form this I, the incidence correspondence of pairs of a line and an X such that the line is contained in X, okay? And then, you know, we can project, we have two projections. We can either forget the information to X or we can forget the information to L, and then I'll call one of them the first projection. That goes to the space of lines. So that's the Grassmannian of lines, and the other side, it goes to the space of hypersurfaces. And how do you think about the space of hypersurfaces? You know, every hypersurface is defined by a single equation. You know, something like, you know, if you're in P2 or something like this, it's defined by something like that, x squared minus yz or something like this, right? So, you know, you can think of the space of hypersurfaces by the coefficients defining the hypersurface. And then, you know, if you have a coefficient of degree, equation of degree D in n plus 1 variables, then you can count how many monomials there are. There are n plus D choose D such monomials. And then, so that means that you can think of the space of hypersurfaces projective n plus D choose D minus 1 space, where, like, you know, you're parameterizing the hypersurface by the coefficients, the equation that define it. And of course, you know, you can scale all these coefficients simultaneously without changing the zero locus. So you can think of this thing as these coefficients up to scaling. All right, so then if we have a hypersurface X here, right, then pi2 inverse of this X, right, is precisely the lines that are contained in X. So that's what we want to understand. You see, the main problem is that that's hard to understand. And the advantage of considering this incidence correspondence is that it linearizes the problem. If now, on the other hand, I look at the other projection, then that projection is not that hard to understand. So the Grassmannian of lines in projector space is a nice homogeneous variety, and the hypersurface of degree D that contain a given line is a projective space. It's a linear space. So it's easy to understand. So let's see what happens. So let me take my favorite line, right? I can always choose coordinates so that that line has equations x2 xn equals 0, right? So now what does that mean for a hypersurface of degree D to contain this line? What it means is that if I have the equation f defining x and I set, you know, and I set, x2, and x2 dot 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 xn equal to 0, then this has to be identically 0, right? That's what it means for the hypersurface cone to contain the line, right? Well, what does that mean? Well, look at the expansion of that thing. If I set x2 up to xn equals 0, I have to get 0. So that means that there should be no monomials, right? Not involving at least one of x2 through xn. So in other words, the coefficient of x naught to the d, x naught to the d minus 1, x1 dot 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 x1 to the d have to be all 0. But you see, these are linear conditions. In the, you are just setting, you have your general equation here, and you are setting some of the coefficients equal to 0. These are all nice linear equations, and they're d+1 linear equations, and they're clearly independent, right? So that you see that the inverse image of a line, the hypersurfaces that contain a given line, is just a nice projective space. Okay. Now from this, we can now learn a lot about the geometry of I, right? So like we know the dimension of this Grassmannian. The dimension of this Grassmannian is 2 times n minus 1. And the fibers of all these over every line is some projective space. From this, it follows that we can compute the dimension of I, and that I is irreducible, right? That's the theorem on the dimension of fibers, if you want. And you see that the dimension is 2n minus 3 minus d plus n plus d choose d minus 1. Again, it's not, the actual numbers don't matter in like, or they matter a little bit, but you can do it, and it's not that hard. Okay, so in particular, we learn something. So you see, if this d is bigger than 2n minus 3, right? So that this part is negative, right? Then you see the dimension of this incidence correspondence. Let me go up. The dimension of this incidence correspondence is less than the dimension of this projective space. So one thing that you learn is that in that case, pi2 cannot be surjective, right? So what that means is that if I take a random point here, right, if I miss the image, then the inverse image of pi2 is empty, right? So that in particular, that kind of hypersurfaces contain no lines. So what we learn from this is that, if d is bigger than 2n minus 3, then the general hypersurface does not contain any lines. Okay, that's the first thing that we learn. So, if in P3, I give you an equation with degree bigger than 4 or more, and then, if I somehow chose these coefficients sufficiently randomly, then that surface will not contain any lines. But of course, there are always hypersurfaces that do contain lines, right? I mean, if you write, for instance, the Fermat, right? If you write this thing x naught to the d minus x1 to the d plus x2 to the d minus x3 to the d and so on and so forth, right? You can always, then there will always be some lines. Like for instance, you can make like x naught be x1, x2 be x3, and all the higher coefficients be 0, and that will be a line. So there are always hypersurfaces that contain lines, no matter what the degree. But if the degree is at least 2n minus 3, the general one doesn't. And we can say a little bit more, right? I actually want to say is that, I want to say that like this map behaves the way you would like it to behave. In other words, we have I, right? We have I here. We have that if the dimension of I is bigger than this n plus d, choose d minus 1, then you see the generic fiber has the dimension I minus this dimension. In other words, I want to say that there is a 2n minus 3 minus d dimensional family of lines. Now you see, by the theorem on the dimension of fibers, what you have to do is you need to show that for one line, that is the dimension. And if you do that, then you see then, just by the way maps between projective varieties work, as that you get it right. So like, let's work it out. So I want to say that if you give me L, then I want to say that there exists a hypersurface X containing this L, where the local structure of the space of lines around in this hypersurface has the expected dimension. And as we said before, right, how do I figure that out? What I need to compute is, of course, the global sections of the normal bundle of the line in X, or if you want, the splitting type of the normal bundle. Splitting type of the normal bundle of the line in X. If this is as balanced as possible, then it means that the space has the correct dimensions. That's what we need to show. Okay, so how do we do it? We need to compute this normal bundle. So remember, the theme of my lectures is normal bundles of curves and varieties, right? That's what we are talking about. And in some sense, you can go a long way if you can understand this normal bundle. So let's understand this normal bundle. All right. So we already know the normal bundle of the line in projector space. We talked about this before. That's last time. So that's O of 1 to the n minus 1. And we understand the normal bundle of X in Pn, right? That's O of d. So restricted to the line is O of d. So then you see the normal bundle of the line in X is the kernel of the map that maps the normal bundle of the line in projector space to the normal bundle of X in Pn restricted to the line. And then the question is, what is this map? You see, this map is not that hard to understand. So let's write it down, right? You can write your F, right? Say that the line has, again, our line has equation x naught to xn is equal to 0, right? Write your F as x2 f2 plus x3 f3 dot xn fn. If you want mods, I mean, maybe this is not unique, of course, but maybe let me say this mods, x2 dot xn square. Okay, then it's unique if you do it mods that, right? And now what you can do is that this map is just basically given by, taking f2, f3, fn and restricting it to the line. So now what we need to do is we need to make sure that if I choose somehow sufficiently general f2, f3, fn, then this normal bundle is balanced. And you know how to do that from last time, right? So what we need to say is that the relations among these entries is what you think it is, right? And then, so what you do is, okay, so you take d minus 1, you divide it by n minus 1, say that there is a q and the remainder. So this is the quotient and the remainder. As usual, this is by the Euclidean algorithm. So r is less than q and bigger than or equal to 0, right? Then you see what you can do is you can choose these restrictions to look like this. But basically, maybe it's just easier to pretend that r is equal to 0 and then you can fix it. So then basically what you do is you decrease it by q each time. So if you decrease it by q each time, then you see, then you have the then you have then you see what the relations are, right? And then the relations are as equal as possible. And if it's like, if there is a remainder, then you decrease it by q once and q plus 1 once, by q once by q plus 1 once, so that the relations are as close as possible in degree, right? And if you do that, then it's easy to see that the relations are between consecutive triples of columns again, and they have equal as possible degrees, so that you see that the kernel is again balanced. Okay, that's some computation. You can do it for yourself. But what's the upshot? The upshot is this. What we learn from this calculation, if x is a general hypersurface of degree d in projector space, and if d is bigger than 2n minus 3, then x doesn't contain any lines. And if d is less than or equal to 2n minus 3, then it contains a 2n minus 3 minus d dimensional family of lines. So that, up to degree 2n minus 3, the hypersurfaces all contain lines. And the general one contains the expected dimensional family of lines. And then once the degree is bigger, then it shouldn't contain any lines. Okay? So that's the basic calculation for today that we want to generalize, right? So there are still many questions here, and very important open questions. So let me just mention them so that maybe some of you can work on them. You can always ask, how about special hypersurfaces? It's true that the general hypersurface sufficiently large degree doesn't contain any lines, but special ones might. So here is, for instance, the question, suppose that I have a smooth surface in P3 of degree at least 4, okay? Then, you can easily show that it can contain at most finitely many lines. But the question is, what's the maximum possible? So this is known for degree 4. The maximum possible is 64 lines, right? But starting with degree 5, we don't know what the maximum possible is. And by the way, when I'm doing this, when I'm having this discussion, I'm over the complex numbers. You could also ask about other fields. So for instance, one of the most famous theorems of algebraic geometry is that a smooth cubic surface over the complex numbers contains 27 lines, right? Every smooth cubic surface contains 27 lines. But you see, over other fields, like over the reals, for instance, it can have different numbers of lines, right? Not all these lines, say that you have a cubic defined over a real, have to be defined over the reals, right? So you can also ask the question, how about the other fields? Like for instance, like over some finite characteristics, there might be more than the expected number of lines and so on and so forth. There are some bounds, like there are bounds due to Segre that says that the number of lines is bounded by roughly 11d squared. Let me not bother with the exact bound is, but roughly bounded by 11d squares. And there have been modern improvements on this. But except for finitely many degrees, the Fermat, which has this equation, right? X0 to the d, x1 to the d, x3 to the d, which has also 3d square lines, is the best known. Like how are the lines are, like, what you can do is you can send x0 to a dth root of unity minus 1 times x1 and x2 to a dth root of unity times x3. And then, you have d choices for what this is, d choices for that, you get d square, and then, you can swap the indices, right? So you get 3d square lines. Those are the only lines on the surface, right? It's a good exercise to check that if you haven't done it before. And, for all but a few degrees, this is the surface that we know with the largest number of lines. But is it really the best? Can you beat it? We don't know. So, even like this kind of basic question is open. The other interesting question is that, you see, the general surface, hypersurface has 2n minus 3 minus d dimensional family of lines. But there can certainly be special hypersurfaces with more lines. Again, let me take the Fermat, or, really what you should take is like a hypersurface that has a hyperplane section, which is a cone. So look at your Fermat like this, right? If I look at the hyperplane section, x0 equals x1, this is the tangent hyperplane at the point 1, 1, 0, 0, 0. Then that hyperplane intersects this hypersurface in a cone. So like if you've set x0 and x1 equal to 0, then you have the smaller dimensional Fermat, x2 to the d xn to the d is equal to 0. And this is a cone with vertex at this point. So you see, there are all these lines on this hypersurface, and the dimension of the lines is at least, like, this is an n minus 3 dimensional family of lines, right? Because in this Pn minus 2, I have this hypersurface, which has dimension n minus 3. And for every point of that, I get a line, right? So altogether, I have at least an n minus 3 dimensional family of lines, right? And you see that 2n minus 3 minus d is less than n minus 3 if n is bigger than d. So that you see that the moment d is at least n, right, you can have smooth hypersurfaces that have more than the expected dimension family of lines. But there are no known examples in the Final range. So like, then here is the de Jong-de Bar conjecture, which says that if you have a smooth hypersurface of degree d less than or equal to n, so this goes under the Final range, right? Because these hypersurfaces are Final varieties, then the conjecture is that then x actually has the correct dimensional family of lines. And this is still open, and the best result I know is due to Beheshti and Riedel, which says that if instead of d less than n, you just say roughly d is less than n over 2, then the conjecture is correct. Okay. But in this range, we don't know it. Between roughly n/2 and n, we don't know the conjecture still. Okay. So, even lines and hypersurfaces have lots of open questions. So like I want to make that clear. Okay. All right, so that was a discussion of lines, but it doesn't end there. So once you do lines, then you can say, okay, how about higher degree curves? And let me concentrate again on higher degree rational curves for today. Higher degree rational curves. So let's do a bogus count. So let's do the same kind of bogus. The previous count was not bogus. The previous 4 lines, it was correct. But now let's do a similar count, and this one will be bogus, okay? So let's do it. So say that we have the space of rational curves with degree E in projective space. So we studied the space last time, right? And we said that the dimension of this was E plus 1 times n plus 1 times minus 4. And remember, the way we got this number was that, such a curve was given by n plus 1 polynomials with degree E plus 1. So that was the E plus 1 times n plus 1. And then, we didn't want to parameterize. So we had to quotient out by PGL2 action, changing the parameterization. And, this thing is, the curve is, I can simultaneously scale these coefficients. So that accounted for the minus 4. Okay. So we have the space of rational curves with degree in projective space. I could form the same incidence correspondence. I have the curve of degree E and a hypersurface X such that the hypersurface X contains it. And again, I have 2 projections. Okay. Now, okay, of course, what we want to understand, right? We want to understand pi2 inverse of X. If I take a point, a hypersurface here, those will be the degree E rational curves that are contained in X, right? Now you see, as opposed to the case of lines, then this is no longer, the pi1 is no longer a projective bundle, right? But you can still try to estimate its dimension. So like you see, so what we want to do is if you fix the curve C, right? The fibers is like the curves, the hypersurfaces of degree D that contain that curve. Or if you want, it's like, what are the hypersurfaces of degree D that contain the curve? It's like the degree D equations in the ideal of the curve, right? So I can count the dimension of the space of degree D equations in the ideal of the curve. And the way you usually do that is that you have like the ideal sheaf of your curve twisted by D. It sits as in the structure sheaf of projective space with twisted by D, with the co-kernel being the ideal, with the structure sheaf of the curve twisted by D, right? You see, this one and this one we understand, right? So like, hypersurface of degree D in projective space, right? That we just said is an n plus D choose D dimensional vector space, right? Because, you're choosing polynomials of degree D in n plus 1 variables. And this we understand as well, right? These you are choosing polynomials of degree E times D on P1. So that has dimension ED plus 1. You see, the differences in the case of lines, we knew that this map was surjective. But for the random curve, rational curve, this map does not have to be surjective. But, let's blindly like ignore that point. And then, given any map between 2 vector spaces, they should have maximal rank, right? I mean, you should remember, like, if you teach linear algebra, all your students will tell you that, you count the number of equations and that's the, the number of variables minus the number of equations should be the rank of the matrix, right? Of course, you spend all your course in linear algebra teaching them that's not correct. But of course, in real life, you should always pretend that it's correct, right? At least that will give you a guess. So let's do this. So then you see, if we pretend that this evaluation map is surjective, which it isn't in general, but let's pretend, then you see there's an expected dimension for the fiber of this pi1. Okay? Of course, there will be special curves where this dimension will jump. So I no longer know that this phi is irreducible, but I don't know its dimension. But, I expect something. What I expect is that the phi, so, I expect that there's an expected dimension for this phi, and then, that gives me an expected dimension for pi 2 inverse of x. And this dimension is e times n plus 1 minus d plus n minus 4, okay? This would be correct, of course, if this evaluation map were always surjective, but it isn't. Okay, but nonetheless, okay, so before we go on, so maybe let's stare at this number a little bit. So the first thing that you should notice is that if d is less than or equal to n, right, then this is positive. So that this is the Fano range, right? In the Fano range, this is positive. So that as E increases, the dimension of the space of rational curves increases. One thing that I should say before we go on, this is a bogus calculation, but it is a lower bound on the dimension of the space of rational curves. So this is a lower bound. Despite the fact that it's being bogus, it's a lower bound because you know that the ranks can jump, but they jump in the right way. So like, if you have that many equations, the rank can be larger, but not smaller, yeah? Okay, so this is a lower bound on every component of the space of rational curves on X of degree E, right? And one thing that you see is that if D is less than N, then this is growing with, yeah? So that's the Fano range. Then the Calabi-Yau range, which is D equals to N plus 1, then this thing drops out, right? And then the dimension of these spaces should be constant, right? They're always N minus 4. And then if D is bigger than N plus 1, so that this is negative, right? There should be only finitely many E where this number is non-negative, okay? Right? And furthermore, if D is bigger than 2N minus 3, the quantity is always negative, okay? All right, so then this leads to a conjecture. This is a conjecture of many, many people. So, the main people are like Clemens, Wezand, and myself, and Joe Harris, and Jason Starr. And the conjecture is like this. Suppose that ND is not 3, 4. So I don't have a quartic surface in P3. Then the conjecture is that then the dimension of the space of rational curves of degree E on a general hypersurface degree D and Pn is given by this expected number, okay? Again, I mean, we did a bogus count, and this bogus count is leading to this conjecture. So I'll say a few words about what's known about this conjecture. So as we said, you see, there are four ranges here. There is the Fano range, right? When there are lots of rational curves. There is sort of the Calabi-Yau range where the dimension of these spaces is constant. And there is like a range where D is sufficiently large that there are no rational curves. And sort of there's an intermediate range where there aren't that many curves, but some rational curves, okay? So there are these roughly four ranges. So let me tell you what's known. So first of all, like, there is work of Ein, Wazan, Pacienza, and many people. So this goes sort of like uses ideas of hyperbolicity, and that will be sort of my lecture next time, right? I will talk about hyperbolicity next time. But so in this range, if D is bigger than 2n minus 3, like what Ein proves is that basically, every subvariety of a very general hypersurface is of general type. So that means that there are no rational curves, there are no elliptic curves, no abelian varieties, anything like that. Okay, so the results in this, and then this was later improved. I mean, the bounds in Ein were one-off, and then Wazan Pacienza improved the bounds to make it the sharp one, and so on and so forth. But the basic theorem here is that if D is at least 2n minus 3 and n is at least 4, then the very general hypersurface contains no rational curves whatsoever. So that, in other words, this conjecture is correct in this kind of range. Okay? Then there is the Fano range, and this is a theorem of many people: Harris, Roth, Starr, Beheshti, Kumar, Riedel, Yang. So, you know, roughly for the history, Harrison, Roth, and Starr first proved this for degrees roughly n/2. Beheshti and Kumar did roughly 2/3 n, and then Riedel Yang finally did it in this range. So not entirely the final range, but if you make like d be less than or equal to n-2, then actually the space of rational curves is irreducible and of this expected dimension. Okay. How about the intermediate range? The intermediate range is really the hardest because, like, you know, when you have a lot of rational curves, you have some techniques to get your hands on the space of rational curves. When you have no rational curves, you know, then it's easy to tell that you have no rational curves. The hardest is when you have some rational curves, but not too many. Okay. And again, here there are some statements. So Clemens, Ran, Pachians, and Eric Riedel and myself. And so this does at least the line range case. So like if you go back to this number, right? And if you make E be 1 and ask when is this thing greater than or equal to 0, then you get roughly something that's no, when you make E equals 2 and you ask when is this thing still less than or equal to 0, then you get something roughly like, you know, 2/3 D, like, you know, 2/3 n. So, you know, when D is roughly 2/3 n, then you will have conics. But sort of between 3 Hells n. When D is roughly 3 Hells n, so there's a 2 there and a 3 in the end. So, like, you know, if you make E equal 2 and ask when is this thing greater than or equal to 0, so you know, ignoring the constants, like, you know, when D is roughly 3 Hells n, less than 3 Hells n, then you will have conics. Okay, so past that point, you expect only lines, and then, you know, when you make E equals 3, so then roughly 4/3 D, roughly 4/3, and then you expect cubic curves and so on and so forth, right? But so the line range is known, and, you know, the sharp results are again due to Eric and myself. And then the statement is like this, that if you have a very general hypersurface degree greater than 3n/2, then, you know, up to the degree being 2n-3, right, they will contain lines. But those are the only rational curves that contains lines, but no other rational curves. And I should mention that recently Abe has made some progress in the conic range. Yeah, I didn't write the exact statement, but there are some really exciting new results about understanding the conic range. So that would be between, you know, 4/3 and 3 Hells, like roughly 4/3 and to 3 Hells. And what you want to say is that there are only conics and lines, but no other rational curves. But, you know, we don't even know that, you know, if you have a hypersurface degree bigger than n+1, that there are only finitely many rational curves, like finitely many degrees of rational curves. So, you know, that's already an interesting question to answer. Anyway, I thought that, like, you know, I shouldn't try to give a proof, like, you know, I thought that I should try to give you a proof of one of these theorems, or at least sketch a proof of one of these theorems. But then I thought, okay, like, it's going to get messy with all these indices. So let me sketch the proof of a simpler theorem, but it contains most of the ideas in the final range. Okay, you know, you have to be a little bit more clever to you know, do it, but, you know, most of the basic ideas are there. So let me just sort of sketch the argument for that so that you see what kinds of techniques go into it. Okay. All right, so this is the theorem of Jason, Starr, and myself, which says the following thing. So I have a cubic hypersurface, a degree 3 hypersurface. Okay, in projective space, and then the dimension is at least 4. Okay, then I want to say that, and this is a smooth cubic hypersurface, then the statement is that the space of rational curves on this of any degree is irreducible and it has the correct dimension. Okay, so like, you know, this is a little bit different than the previous theorems. So, like, you know, it's a little bit stronger because it's saying that this is true for every smooth cubic hypersurface. Okay, The other ones, like, you know, we've seen examples where things can be messed up, right? And notice that this stronger statement, like for the conserved space, is actually false if you take the degree bigger than 3, because then there can be special smooth hypersurfaces, like you know, having conical hyperplane sections and things like this. It is still possible that the closure of the locus of smooth curves is irreducible, you know, roughly for the degree, I believe, less than n/2 or something like that, right? That's not known. But, you know, the point here is that, oops, am I deleting some of these things? The point here is that the statement holds for every smooth cubic hypersurface of dimension at least 4. Okay, but the idea is, I mean, you can use almost the identical argument to do the Harris-Roth-Star statement, and you know, the Riedel-Yang statement requires a little bit more analysis, but you know, let's just not worry about this. Let's just, I mean, my goal here is to teach you like a few things to get you started. So let's do it like this. So how does the proof work? So I want to say that the space of rational curves is irreducible, and I want to count its dimension. Okay, let's get the page. Okay, so the idea is this. What we are going to say, I think I had this. There are 2 points to make. So let's start with the points to make. The first point is that we have a lower bound on every component, right? This number that we found, whatever it was, this number that we have, e times n-2 plus n-4. So the first observation is that e times n-2 plus n-4, this is a lower bound on the dimension. Okay, that's the first observation. The second observation, right? So we already have a lower bound on the dimension. The second observation is that, you see, we compactified the space, right? So, and we know what's on the boundary. On the boundary of the space, right, I have curves that break. So this is I degree d minus I. So the way we are going to do this, we are going to do induction on the degree of the curves. This should be on the degree of the curves, right? So now you see, suppose that I know, like, you see, here is the main point. We already know that if I look at projective space, right, this is irreducible, and we know that the boundary is a divisor. Remember, the boundary were like when the curve broke into 2 pieces, this was degree I, this was degree d minus I, and this is a divisor. So now you see, if you look at the space M00 xe, right? This of course sits in M00 Pn, right? And now the question that you can ask is that if I have this divisor, how does it intersect the space? You see, because this is a divisor, the Krull-Hauptedelsatz tells you that, you know, like, you know, this thing is defined by an equation locally. So this equation can be identically 0 on this, right? Or it could define this, or it can cut out a divisor, or, you know, it could be identically a unit, right? So those are the 3 possibilities. In other words, what that says that D intersect this M00 xe, or a component. So let's say that we have a component in here. Say that we have a component in here, D intersect this component, right, can be 2 things. C, D can contain it, D could be disjoint from it, right? Or C intersect D as a divisor, right? That's what things defined by one equation, Krull-Hauptedelsatz, the you know, 0 divisors theorem, or whatever they call it, yeah, says that, you know, if you have a divisor, it, you know, you intersect the space with the divisor, it could be contained in the divisor, it could miss the divisor, or it intersects within the divisor, Okay, so then the idea is that suppose that I know the space of rational curves degree I and E minus I. It's keep making this mistake, E minus I, right? Then, like, you know, I can say what's the dimension of this divisor. And if I can estimate the dimension of this divisor and show that it's one less than this, then I win, right? If I can show that this divisor is one less than this, then it means that because there's a lower bound on the dimension of every component, then you know that, first of all, you're not contained in the divisor. And so you have to be a divisor in there. And if the dimension is one less, then the dimension of the component has to be this, right? So that's the idea that you do. You do induction on the degree of the curve, and using the fact that in the conserved space and projective space, the reducible curves form divisors, okay? All right, but if you want to make this thing work, what's the thing that you need to do? You need to understand lines first. You know, that's the base case for induction. And this is always the case. And the problem that makes, like, you know, the bound n/2 roughly comes from, you know, for the base case on the induction line, when lines are enough, right, then you can make things work. And that gives you the Harris-Roth-Stars theorem. Now, if you want to do the Beheshti-Kumar, then you have to also understand conics. And then if you want to do the Riedel thing, you might have to go to degree roughly n or something, yeah? But anyway, so the base cases of these things are hard usually. Lines being the easiest. In the case of cubics, lines are very easy. So like, so again, we have the normal bundle of the line. And again, what controls the geometry is always the normal bundle. So that's what you have to understand. The normal bundle of the line in X sits in the normal bundle of the line in projective space, the co-kernel being the normal bundle of X restricted to the line, right? So then you see here we have a rank n-2 bundle of degree n-4, and you can ask, how does it split? And it's a sub-bundle of O of 1, so like, you know, the largest summand has to be a 1. Well, there are only two ways it can split. It can be n-4 copies of O of 1 and 2 copies of O, or it could be n-3 copies of O of 1 and a copy of O of -1. Okay, so you see from this you learn that both of these things have age not equal to 2n-6 and age 1 equal to 0. So like we are in a really good shape in this case, right? And you see this degree 3 is important here, right? If I make this 4 or 5 or whatever, then the number of possible splitting types increases, and there are become splitting types where there starts becoming age 1, right? So like, you know, then not all the spaces of lines on every hypersurface is smooth, but on any smooth cubic hypersurface, all spaces of lines are smooth. And that's what's special about cubics, okay? So you see the space of lines is smooth of dimension 2n-6, and it's irreducible because it's connected. The space of lines is, you know, on the in the Fano range is always connected. Well, most of the time it's connected, let me say. So you know, the connectedness is easy because, like, you see, like you can ask what are the spaces of lines passing through a point, and it's given by a complete intersection. If the number of equations that you have is small, as in the case of cubics, then that's going to be connected. Okay, so you see that the space of lines is very nice on the cubic. But you see, we have to understand a little bit more than the space of lines. So you see, the way we are playing this game is that we are breaking the curve, right? And the danger that you run into is that maybe there are some special points on your variety where many lines pass to that point. And then, you know, if you have too many lines passing through one point, then you can form many pairs of these things to form a conic. So then you see, it's not just enough to know the space of lines. We also want to know that the space of lines that pass through a point has the expected dimension, okay? So that we can do this inductive gluing procedure. So we need more. We need to know that the space of lines passing through a point has dimension n-4, okay? And again, these dimension estimates, of course, when you're really proving, you have to keep track of them. Because this is on Zoom and we are doing all these things, I don't want to keep track of them too much. Yeah, I'll leave it as an exercise, or you can look in the papers and find the estimates. So I'm not going to write down all the numerics too much. Okay, you just have to take my word for it that it works out. So you see, in the case of cubics, that's really nice. In fact, this dimension is correct, except possibly for finitely many points. Okay, so in other words, on your cubic hypersurface, the space of lines that pass through every point is n-4 dimensional. On some special cubic hypersurfaces, there may be finitely many points. And instead of, through those points, instead of there being n-4, then there ends up being n-3 dimensional family. Okay, so in other words, you know, for most points, for almost all the finitely many points, the space of lines to that point is as expected. And through these finitely many points, it jumps by one. Okay. And then you see, in order to do the Eric-Riedel, the Riedel-Yang theorem, right? Then you need to sort of look at some singular hypersurfaces and just look at, you know, the locus where like the dimension of rational curves of a given degree jumps by a certain amount. Like, and you need to do this kind of estimate. So, you know, that idea is already present in this proof as well. So, okay, so now let's think about this. When can this jump? So let me take my cubic, let me take my points so that it has these equations. Let me expand my cubic around this point so that it looks like this, right? Now, the space of lines is given by, you know, if I have a line to that point that looks like this, A naught has to be 0, right? So that it lies in the tangent hyperplane to this. And then, you know, if I plug in these things for F2 and F3, I need to get 0. So that you see that the space of lines through a point, right, is in this Pn minus 2. In this Pn minus 2, it's given by the vanishing of two equations, F2 and F3. The quadratic form of the expansion and the cubic form, like, you know, you take the Taylor expansion, it has the degree 2 term and the degree 3 term, and in that Pn minus 2, this degree 2 term and the degree 3 term have to vanish. And then, you know, typically what you would expect, that you would expect that to be n-4 dimensional, right? The only time when it's not n-4 dimensional is like, you know, these have to have a common component. This quadratic and cubic equation have to have a common component, or has to be identically 0, right? When I restrict it to the tangent hyperplane. Anyway, you can analyze these cases and then you see that the only real possibility is when this F2 is identically 0. I mean, in the other cases, it turns out that the cubic has singular points. You can just write it down. So now, like you see, now what we need to say is that like there can be only finitely many points where you expand the Taylor expansion that the quadratic form vanishes. But that we know how to do. You see, this quadratic form has a different name in differential geometry and algebraic geometry. It's called the second fundamental form, right? This second fundamental form is the derivative of the Gauss map. So now what's the Gauss map? The Gauss map is the following thing. You have your manifold, and at each point you send it to the tangent space. So if you are in Pn and this is an m-dimensional manifold, right? You get a map to the Grassmannian of m planes in Pn, right? And the derivative of this map is given by the second fundamental form. Now you see, if this derivative is going to vanish along a curve, right, then the Gauss map has to be constant along a curve. But you know, you have a map from X to this Grassmannian. X is Picard rank 1. So if you contract the curve, then it has to be identically constant. So that you see, but that's nonsense, right? I mean, the tangent spaces to a hypersurface cannot be constant, right? Or smooth hypersurface. So anyway, so where you see that, you know, there can be only finitely many points where the second fundamental form can vanish. And that says that, you know, the space of lines can be n-3 dimensional only in finitely many lines, okay? Then we have these remarks that I made. So now we do induction on the degree, okay? So the one other idea that you need is this Mori's band and break argument, right? So this is the famous Mori band and break argument. In this case, what it means is that if I have a one parameter family of rational curves, right, with two fixed points, right, then this curve has to break. Now, what's the reason? Suppose it doesn't break, right? So that I have a one parameter family of rational curves, and these points P and Q give me two sections. Okay, but you see, I mean, this is a P1 bundle over a curve, right? So that, you know, if you have two sections, like, you know, you can't contract two sections without contracting this thing to a curve, right? So we understand these kinds of surfaces well enough. So that means that it can't, like, one of the curves has to be reducible. Okay, so now you see, you make this kind of argument. So what this says is that as long as E minus 1 over E times M plus 1 is bigger than D, right? Then what you do is you look at curves that pass through 2 points, and then you see that the dimension of such things is at least 1. In which case that means that it has to break. And, you know, for our purposes, what this means is that basically you can, in every component of, say, larger than expected dimension or something like this, you can always find curves that break. Okay, and now you just play the game, right? So what you do is that, okay, so let me prove that conics have the right dimension. What you do is, okay, I break my conics, right? So you see, in fact, what you want to prove is that except for the same finitely many points, in fact, you want to prove the more special, more stronger statement that except for these finitely many points, right, the space of rational curves with degree E through every point has the expected dimension, right? Then the kind of game that you play is, okay, like, I want to prove this for conics, right? Let me take a point, and then, you know, there's several cases, like the point could be one of these special points or not. Let's pretend it's not first. Then you see the space of lines to that point has the correct dimension. Then, you know, through one of the points this, I need to choose another line, right? Then I have to add them up and add one, right? And then, you know, there's various possibilities. You know, it could be that this point is one of the special points, or the attaching point is one of the special points, or this line passes through one of the special points, or so on and so forth, right? But in any case, you know, like, you need to do the cases. You do the cases and you see that it works, okay? So that's the basic thing, that, you know, if you look at the reducible ones, they form a codimension 1 space. So that tells you that it has to be, the dimension has to be correct, okay? And like a final point about the irreducibility, how do you get the irreducibility? In fact, what you show is that all components have to contain, you know, the union of chains of lines. And the reason why I'm bringing this up, you see, very often in studying these things, what you need to understand is that if you have a reducible curve, what is the normal bundle of that? So far, we've been talking about, you know, a smooth curve and its normal bundle. But what happens if you have a nodal curve like this? So you have a nodal curve. What is its normal bundle? Okay. So you see, the normal bundle of a nodal curve is, it can be understood. So let me tell you. So say that I have C, which is the union of C1 union C2. Let me look at the normal bundle of C and restrict it to C1. Okay, so I take the normal bundle of the union of the curve and I restrict it to C1. And it's here, it's very important that this is nodal. Okay, I mean, if you have more complicated singularities, then this analysis doesn't work. In fact, it doesn't have to be a bundle anymore, right? But you see, here the statement is this. So this thing is the normal bundle of C1 twisted by, so you see, it's the normal bundle of C1, except that you allow poles, and you twist this thing by the point P, and you make an elementary modification in the direction of the tangent line of C2. Okay, in other words, the way to think about this thing is that you see, you allow So the normal bundle of the union of the curves restricted to one component is, the normal bundle of the component where you allow an additional pole in the direction of the tangent line of the other component. Okay, again, this is a local calculation. You can find it in many places. But you see, in particular, you see what this means is that, if you have a union of lines like this, right? And the normal bundle, where was our lines? And the normal bundles of the lines all look like this, right? Then you see if you put them together, then the normal bundle of the, so you see that the normal bundle doesn't have H1, of the union doesn't have H1. So the consequence is that then that point is a smooth point. But you see, if you had more than one component containing such a thing, it couldn't have been a smooth point. So you learn that, and it has to be irreducible. So that's the basic argument. All right, you see, there is an important problem here. So this description is telling you what the normal bundle of the union restricted to each component is, right? But it doesn't tell you what the identification is. So let me give you an example. Suppose that we have two intersecting lines in Pn, okay? The normal bundle of a line, we already said, is O1 to the n minus 1, okay? So then you see, if I look at the union of this curve, right, and ask what is the normal bundle, what we are saying is it's O1 to the n minus 2, and I get an O of 2, and O of 2 is in the direction, of this line, yeah? And you see the normal bundle of M is still the same, right? And now you see what's not so clear is what is the identification of these two normal bundles at the node. And that is a hard problem. And then it's an important one, and we don't understand it very well. And, it is a problem. And then you see, here, very concretely, what is this question? So you see, I have this line, and then I have over this point, over the node, I have the fiber. But there is a distinguished direction here. There's a distinguished line, which is the O of 2. Similarly, on the other component, at the point P, I have a fiber, and there is an O of 2 there. Then there is a direction coming from this O of 2. You see, the union, right? Like, it matters for the union whether these O of 2s match or not, right? If I knew that these O of 2s did not match and I deformed it, typically what I would get would be like a bundle like this, so that it would be balanced, right? But if they do match, then I can only guarantee that I get an O of 2 to the n minus 2 plus O of 4. In this case, of course, we know that it's this, they match, right? The reason is because we know the normal bundle of a conic, right? I know the normal bundle of a conic is like this. If I take the union of the lines and deform it, this is what I'm going to get instead of this, right? So this identification is not well understood, and this is a significant problem, okay? So, you can ask, for instance, like, if you have, anyway, that's the next question that I want to ask. So, all right, so that's the sketch of the argument. Again, I didn't do all the calculations, just, I think that probably better if you do it yourself at home than me putting lots more indices than I'm already putting, okay? Any questions?
When you say the normal bundle of C, do you mean after deforming it, or?
Oh, yes, if of a deformation, yes, of the conic. The I'm C here is a conic. Let me call it B for the conic. Yeah. So, if you are deformed, if you smooth that node out so that you get the conic, then the normal bundle is like this. That's because these O of 2s match. Typically what you expect is that if you have a random union of curves, you want to say that the positive directions in these two fibers are as transverse as possible. The point of this example is that it doesn't have to be. Okay. All right. So I want to do one final sort of applications of these normal bundles of rational curves and hypersurfaces, right? And this is the separable rational connectedness. So, up to now, like, I was being a little bit careless about the characteristic of the field. I was mostly thinking that I was working over the complex numbers. But for what I'm going to do next, it's important that we work over arbitrary characteristic, okay? We're working over an algebraically closed field of arbitrary characteristic. So now here is the situation. Suppose that I start with a rational curve of degree E, and let me look at hypersurfaces of degree D containing this curve. And now you see what I want to understand is what's the normal bundle of this curve in X, right? And in particular, I want to say that if X is general enough, then this should be balanced, okay? All right, so now you see, we can understand this to a little bit. We can understand this to a certain extent, okay? So here is the situation. I have my ideal of the hypersurface in Pn, and I have the ideal of the curve in Pn. Now you see, if you have your ideal of the hypersurface in Pn, then it maps to the ideal of the curve in Pn, with the co-kernel being the ideal of the curve in the hypersurface. And I mean, what does this map? This map is a very, very concrete thing, right? Here you have your generator of the ideal of the curve, right? Here you have your X, right? And what you do is this alpha is a way of expressing, right? This alpha as a way of expressing this equation F in terms of the generators of this thing, yeah? So, if you choose like a particular equation, of course, you get an identification of the ideal of X in Pn with O of minus D. All right, so let's apply Hom blank to OC. Then you see this becomes the normal bundle of C and X. This becomes the normal bundle of C and Pn, and this becomes, the normal bundle of X and Pn restricted to C if the curve has degree E. So this is OP1 of ED. Okay, so this map, of course, is just a dual to this. We just dualized, right? The dual to alpha. Okay. So you see, the point is, in other words, the way you should think about this is that each time I have an element in the ideal of the curve in degree D. So this is a degree D equation vanishing on the curve. I get a map psi, right? But I know what the normal bundle of the curve in Pn is. So maybe here, let me assume that this is a smooth rational curve with degree E. Let's assume that this normal bundle is balanced. Yeah. In fact, yeah, or like, maybe it's not balanced, but anyway, so okay, I don't need to do that. Let me start again. So each time I get an equation, I give an equation F vanishing on the curve, you see I get the psi associated to F, which is a homomorphism from the normal bundle of the curve in Pn to this OP1 of ED, right? Basically what you do is you write F in terms of the generator of the curve that gives you this map, and you dualize it, you get that psi, yeah? In other words, you see I have a map from equations vanishing on curve to, let me put an F there. Of course you can't see it. Let me put an F there, right? So you have a map sending this F to the psi of F, which is a homomorphism from the normal bundle of the curve to this OP1 of ED, okay? In other words, okay, you can also, of course, it's a global set. Okay, so now you see, I want to understand this map a little bit better. But so I claim that this map is nothing other than what you think it is, right? So like you see, the way you get the dual of the normal bundle, the way Hartshorne would define it, is that, it's I mod I square, right? That's what the normal bundle is. That's what he will tell you, right? And the way that happens is that you have I squared, the square of the ideal of the curve in Pn and degree D maps to the ideal. Then you get the dual of the normal bundle, right? So you see, it's not so hard to see that this identification sending F to C of F is actually nothing other than this map in the global sections. Again, this is a local calculation. You can do it or look in the papers, right? So that you see that so that you see that this map goes like this. So the importance of this thing is that we understand the kernel of this map. So the kernel of this map is H0 of IC and PN twist square. Yeah. Okay, so here is the theorem. The theorem says that this map is surjective. This map phi is surjective in various cases. So, so if this is a rational normal curve of degree E less than or equal to n, and the degree D is at least 3, or if this is a curve of degree n plus 1 general enough, and D and n are at least 5. Okay. Now you might ask, why do we care about this? Okay. So let me explain why we care about this, and then when we are done, then hopefully you will appreciate it. Okay. So you see, in some sense, the simplest varieties are rational varieties. So now what's a rational variety? A rational variety is a variety which is birational to Pn. Or if you are just studying function fields, right, is a variety whose function field is, a purely transcendental extension, right? So, birational varieties are classified by their function fields, right? Pn's function field is the purely transcendental extension. So, a variety is a rational variety is something that, is birational to Pn. The way you should think about this is, your early mathematical life, when you were doing calculus or like doing areas and whatever, right? Any equation that you wrote down was like this, right? I mean, it had a parameterization by like the plane or something like this. Okay, these are the important varieties that you deal with in life a lot of times, yeah? You can weaken this thing a little bit and talk about unirational varieties. What's a unirational variety? A unirational variety is a variety that you can parameterize by Pn, but it's not necessarily a one-to-one parameterization. In other words, you have a dominant map from Pn to X, rational map, but there might not be an inverse. Okay, it might not be one-to-one. This means that, like, when you were doing your integral or whatever, you parameterize this thing, but you do the 2-to-1. So when you do the integral, you remember to divide by 2 at the end or something. Okay. All right. In dimension 1 over the complex numbers, these are the same. Rational curves and unirational curves are just P1, where the genus is 0. So these are determined by an invariant. In dimension 2, again, over the complex numbers, this is true again. Rational and unirational are the same. And this is a Castelnuovo's theorem that tells you that you can characterize rational varieties by just some invariants. I mean, Q and PG have to be 0, and anyway, it's enough to say the 12th plurigenus and Q are 0 or something like this. Okay. Starting in dimension 3, this is false. Unirationality no longer, I mean, rationality obviously always implies unirationality. I mean, if you have a rational map like this and a birational map like this, right? In particular, you have a birational map like this. You have a rational dominant map like this. So rationality implies unirationality, but starting in dimension 3, it's not true. There are unirational varieties that are not rational. I mean, there are many famous examples of this thing. Some you might have heard of the Clemens-Griffiths example, which says that a smooth cubic threefold is not rational, but it is unirational. There are other examples due to Art and Mumford or Iskowski-Manin, and this is a whole slew of these examples, okay? And especially recently, due to work of Voisin and Kolyotelin and Pirutka and Schroeder and many people, it's been, this field is getting a lot of attention. But the point is that, these rationality and unirationality are very hard to understand. They're very difficult problems. It's in the 90s, Kolar, Mioka, Mori suggested an alternative that's easier to study. And this is rational connectedness, okay? Let's understand this. What does it mean for a variety to be rationally connected? Again, let me pretend I'm over the complex numbers and my variety is smooth, okay? Then you can define this thing in various ways. One is that you can say that through any two general points, there's a chain of rational curves. It turns out to be equivalent to saying that through any 2 points, there's a smooth rational, the image of a P1 to it and things like this. So, let's maybe be a little bit loose and say that given 2 points, there exists a rational curve passing through them. Okay, and of course, the main example of such things, the big example is Mori's celebrated theorem that says the Final varieties. So let me remind you, a variety is final if the canonical bundle is anti-ample. So if minus kx is ample, then you call these things Final varieties. They are very important in birational geometry because, like, you know, when you run the minimal model program, they are one of the main building blocks of other varieties. So these Final varieties are very important. And, you know, it's in trying to understand the birational classification of higher dimensional varieties, they came up naturally. And, you know, Mori's celebrated theorem is that they are rationally connected. By the way, there is still no characteristic zero proof of the statement. You know, it would be really nice to find a characteristic zero proof of the statement. But, you know, the way Mori's argument works is it goes through characteristic P. Okay, let me just warn you a tiny bit that you need to be a little bit careful when X is singular and the characteristic is not zero. For instance, this rationally chain connectedness and rational connectedness need not be the same if, you know, the variety is singular. Like, for instance, you can take a cone over an irrational curve, right? Then this is rationally chain connected. If you have a point here and a point there, then you take a line that goes to the vertex and you take a line that goes to the vertex, and then you can connect it by two lines. But of course, you can't connect them by a smooth rational curve like this, right? Because, you know, if you have the smooth rational curve like this, then you could project it to this irrational curve. And, you know, a genus zero curve cannot map to a higher genus curve and things like this. So you have to be a little bit careful about these things if you have singularities. And you need to be also careful if you're in characteristic P. You know, so, you know, I sort of colloquially told you that the rationally connected variety is a variety where there's a P1 through any 2 points, right? But what does that really mean? If you want to make it a little bit more precise, what you would say is that you have a space of rational curves with 2-pointed rational curves. And then, you know, the evaluation map at P and Q map to X cross X, and you want that map to be dominant or something like this. You know, you would say it a little bit more formally, yeah. You see, in characteristic P, then the question arises whether this map is separable. Yeah, the map might not be separable, and if it's not separable, then it's not, the good properties don't work so well. Yeah, and so you call something separably rationally connected if this map is actually separable. Okay. And then there's an important question of Janos Kolar, which asks whether every smooth Final variety is separably rationally connected. Okay. Okay. Final fact that you need to know. By the way, I should have said this, but Janos has a beautiful book on rational curves. It's called something like Rational Curves in Algebraic Varieties or something like this. I recommend reading that book if you're interested in any of these topics. It's a beautiful book. But, you know, the basic fact about this is that a variety is separably rationally connected if it contains a very free rational curve. And what does that mean? If you have a curve whose normal bundle, you know, it splits like this, if all the AIs are bigger than 0, if you can find one curve like this, then your variety is separably rationally connected. And, you know, if you want sort of a, like, what's the reason for this thing? Because, you know, what you can do is, like, I mean, you know, the way you should think about this is that, you know, like, you know, if you look at the deformations of this curve that fix a point, the deformations of this curve fixing a point look like this, right? And if I look at this, all the summands with this are still greater than or equal to 0. So, like, you know, there is no H1, like, you know the dimension of that thing, and you can see that, like, you know, deformations of the curve passing to that point still cover all of X essentially. So, like, you know, that sort of gives you a way of sort of connecting that point to all the curves. Anyway, you need to be a little bit more careful about this, but, you know, the basic idea is that if this bundle is very positive, then, you know, you can deform this curve while fixing some points on the curve. Okay, so that you see, in other words, in order to answer this kind of question, what we need to do is we need to again find curves with normal bundles that split positively. Okay, but you see, I mean, that's where this comes in. So, you know, that's where the surjectivity of this map comes in. Let me explain a little bit. Okay, so here is the theorem. So suppose that you have integers at least 2, sequence of positive integers, and let X be a general Final complete intersection of these degrees. Okay, so then the statement is that if the decays are at least 3, if dk is at least 3, the last one is at least 3, I wrote them in increasing order, then X contains a rational curve with balanced normal bundle for every degree between 1 and n. And, you know, if all of the numbers are 2, then, you know, there's a similar statement, but the bound is 1 off. Okay. Now, what's the corollary of this thing? So what we are saying is that if you have a Final complete intersection, right, then you can find balanced rational curve, but rational curves with balanced normal bundle. Okay. So then you see, what does that mean? So let's do a calculation. So in particular, if you have a general complete intersection of these degrees, then you have a very free rational curve, provided that this E is bigger than this. Yeah. And then the consequence, of course, is the theorem of Tian, Chile-Chen, and Yizhu, which says that a general Final complete intersection in projective space is separably rationally connected. So, you know, this is telling you that, you know, at least for high complete intersection, Final complete intersections in projective space, right? This is a large family of Final varieties. At least the general one is separably rationally connected. Okay, so this is sort of a positive answer to the question of János in this case. Okay. All right. So now what's the point? Let's do the point. Okay. So the point is like this. So I want to compute the normal bundle of this curve. Let's compute the degree. The tangent bundle of X, we know what the degree of the tangent bundle is, right? The tangent bundle has degree, like, you know, the Chern, like the first Chern class of the tangent bundle of X, right, has degree n+1 minus the sum of these di's. Okay, so the degree of this restriction is E times that, and the degree of the tangent bundle of P1 is 2. So altogether, you see, we know what happens. So we have the normal bundle of the curve in X has this degree, and its rank is n minus k minus 1, right? If we know that this is balanced, right? And if we know that this is balanced, then we know what the degrees are, right? I divide the degree by the rank, and then, you know, that number is like, you know, it's a direct sum of those numbers, or what it really is that, you know, you divide it, you look at the remainder, and it's, you know, some number of the quotients and some number of the quotients plus 1, the remainder number of quotients plus 1. Yeah. So in other words, if this quotient is at least 1, right, and the curve is balanced, then I get a very free curve, right? And anyway, if you do the numerics, then, you know, it boils down to this numerics. Okay, the numerics don't matter so much. So in particular, if we have a balanced curve, right, of the correct degree, then we get that we have a very free rational curve. And then, as I said, if you have a very free rational curve, then X is separably rationally connected. So that's why we care about how balanced this normal bundle is. Okay, so now suppose that the map that you have from this H0 of IC of t to this home is surjective. Okay, what that means is that you see every possible homomorphism from the normal bundle to ED occurs for some choice of equation of degree D containing the curve, right? Okay, so let's look at that, what that means. So now if I look at this normal bundle of the curve in Pn, right, we know what that is. We computed this last time. It's like E plus 2 E minus 1 times O of En minus E times. So now I'm looking at homomorphisms from this normal bundle that we know to this bundle, right? And the question is the general kernel balanced? If the general kernel is balanced, then, and this map is surjective, then I can find an equation such that the normal bundle is balanced. The fact that the general kernel is balanced is relatively easy. This is a basic Bertini type theorem. So you see, you know, so it's enough to produce for you one map where the kernel is balanced, and the general one will be balanced, right? So we need to see that it's balanced, but you know, play this game. Suppose that I have a map from a direct sum of AIs to some bundle of T, right? It doesn't even matter what the particular things are. If AI, the sum of the AIs minus T divided by R minus 1 is less than or equal to the minimum one, then the kernel of the general map is going to be balanced. And again, as I said, it's enough to sort of exhibit one such. You see, the reason is this: look at the balanced kernel, right? The point is that the degree of each of these things, the degree of each of the summands is less than AI. So then the map, so the homomorphisms from this W, which is the balanced kernel, to this V that I want to map to, is globally generated. Then you see, if the homomorphisms between two bundles is globally generated, right? Then for the general homomorphism, then the rank of, like, you know, you can ask, when does the map drop rank? So, you know, you have your W here. This is of rank R minus 1. It's mapping to this V. So the question is, so I have the general phi, it's phi we use, psi, the general psi. When does it drop rank? You know, it drops rank. So the rank becomes R minus 2. It's R minus 1 minus R minus 2. This is a special case. R minus 1 minus R minus 2 times R minus 2. So it drops rank in codimension 2. But because we are on P1, then it means that this map never drops rank. So that's sort of the Bertini type theorem. So if you have a general homomorphism and this Hom bundle is globally generated, then you see you get an inclusion of vector bundles like this for the general homomorphism. But if this is an inclusion of vector bundles, then the co-kernel is a line bundle. And we know what the degree is. It's designed so that the degree is O of D, right? And then you see that then you can take this quotient as your example of the quotient where the kernel is balanced. So then I've exhibited to you one balanced kernel, so then that means that the general one is balanced. So what that means is that if I knew that this map is surjective, then for the general F containing the C, the normal bundle is going to be balanced. Okay, so then we are left to understanding whether this map is surjective, but we can do that, right? So let's go back to where we talked about that map. Where did we talk about that map? You see, what we said is that we described the kernel of this thing, and the kernel of this thing was H0 of IC and PN square, right? So in other words, I want to understand the equations of degree D that are double along the curve. You know, you can really compute this thing. I mean, there are various ways of computing this thing. So in particular, you see, I know this dimension, I know this dimension, and if I know this dimension, right, to say that this map is surjective means that this dimension is the difference. It means that the dimension of this vector space is the same as the dimension of the differences of these vector spaces, right? Because this is the kernel. And, you know, you can compute this dimension and see that it's surjective. There are various ways of doing it. One way of doing it is that you can specialize the curve, for instance, to a union of lines and ask, like, what are hypersurfaces of degree D that are double along these lines and count. So anyway, there are many ways of doing this thing, and you see that this is the expected dimension. The conclusion, of course, is that, again, the conclusion is the positive answer to question of János, which was first proved by Tian, Chen, and Zhu, right? That's a general compound of complete intersection separably rationally connected. Let me finish with some open problems here that, first, a remark that this can be generalized to other varieties. There's no reason to do complete intersections in PI. You can do other Fano families, you can do general Fano complete intersections in Grassmannians, flag varieties, certain weighted projective spaces, and so on and so forth. Let me point out that there are some results to start on with different techniques, right, that work for all complete intersections. I mean, Janusz Kolar's question is, if you have a smooth Fano variety, it should be separately rationally connected. We are saying the general one is. So there is some distance between all smooth ones and the general one. So but there are results to Star and Tian that prove that all smooth complete intersections are separately rationally connected, but then there are some restrictions on the characteristic. The characteristic has to be sufficiently large. In what we did here, there is no restriction on the characteristic. Anyway, so, but there is, this question is still fascinating, and it's still possible that there are special Fano complete intersections that are not separately rationally connected. I'm a little skeptical of that. I think that will not be, but there are other families of Fano varieties, and it might be interesting to look at them and see whether there are any examples that might not be separately rationally connected. I should say that there are special hypersurfaces where this bound we give on the degree is not good enough. You need to take curves of bigger degree to show them they are separately rationally connected. I think if you look at Fermat hypersurfaces in characteristic 2, they give you some trouble. So, it's possible that there are special hypersurfaces that are not separately rationally connected. And it's certainly very interesting to look at other families of Fano varieties. So maybe let me stop there. So next time I'll sort of further push these ideas. And now I'll start talking about higher genus curves and their normal bundles. So far, it's been just rational curves and hyperbolicity and the connection to arithmetic and things like this next time. Let me stop there.
All right. Any question? Okay. Thank you very much, Izzet. And this is the last talk for today. We'll see you tomorrow.